High Energy Lunch Talk. And today our first speaker is Felipe Santos. Felipe graduated from University of São Paulo, and he was also a postdoc at Center for Astrophysics. And right now he's a postdoc at the High Energy Division. And to summarize Felipe's life in one sentence, he loves astrophysics, and he scored 400 pounds. And he plays For the Love of God by Steve Vai.
So today I'll be talking about binary black holes, gas sloshing, and cold fronts in the X-ray halo hosting 4C 3711, a radio galaxy. So here is the list of people involved in this work. So I cannot change. Why? Okay. So I'll start by talking about galaxy clusters. So they are the upper limit of the halo mass function, the most massive structures in the universe. They have masses ranging from 10 to the 14 to 10 to the 15 solar masses. They're very big. They extend to megaparsecs in the sky. And they're mostly made of dark matter, 80% of the mass, but also like hot baryons, 15% of their mass, and cold baryons. So cold baryons are in the form of stars in galaxies and in the intracluster light. The hot baryons is the ICM, this intracluster medium, very hot medium that has been gravitationally shock heated to temperatures of 1 to 10 keV, and it has a very low density, 10 to the minus 2, 10 to the minus 3 particles per centimeter cubic. Because of the very low density, it's optically thin, and this plasma is in a collisional equilibrium state and between electrons and the heavy ions. Most of the emission in the 0.1 to 10 keV band in the X-ray band is due to bremsstrahlung, the electron scattering by the heavy ions. And also there are emission lines due to K and L shell transitions in the heavy ions. So these structures are formed along these cosmic filaments. So as the universe gets older, like denser regions become denser by accreting material, and as they flow to these nodes in this cosmic web, they form the galaxy cluster. The most massive structures are formed in the nodes of these filaments. But in this talk, I'm going to talk also about the supermassive black hole in this galaxy cluster, hosting 4C 3711. So I'm going to give like a short description of the problems and how these supermassive black holes get together. So the idea, the general picture, is that when the galaxy pair becomes like gravitationally bound, they virialize. Dynamical friction and violent relaxation will bring the stellar cores together in the merger remnant, and this will take roughly like a dynamical friction time. As the cores have merged, the stellar cores have merged, and they bring the black holes. They will continue the black holes will continue to experience dynamical friction due to the stellar environment. And this will further like centralize the black holes. And the separation between these two black holes will be determined by the fact that the enclosed mass will be equal to the binary system mass. Okay, and this takes like a Chandrasekhar time scale time for dynamical friction. So the orbit, after this first violent relaxation, the orbit continues to change, the orbit of these binary supermassive black holes, due to dynamical friction, but as time goes by, it becomes the movement is like they have like larger velocities, and the dynamical friction becomes inefficient. So there's this problem called the last parsec problem, which is the difficulty to bring like systems that have just like violently relaxed to this state, to the separations where gravitational radiation can actually make these binary black holes coalesce in less than a Hubble time. And if that is indeed the case, like they should be stalled at ranges of like 0.01 to 10 parsecs. So if that happens, and if the systems are unable to get to the regime where gravitational waves will actually make them coalesce in less than a Hubble time, they should be stalled at like parsec separation, and this would like cause like a dramatic like consequence to gravitational wave detectors because of the frequency. They would be like spiraling, and they would be below the frequency they can actually detect. So from the observational point of view, only 2 kiloparsecs like double black holes have been observed. So one in NGC 6240 at 1 kiloparsec separation, and the other one in this galaxy that we're talking about at a 7 parsec separation. So from the observational point of view, you can look for these binary black holes, supermassive black holes, by looking at the spectral index mapping of the core regions of radioluminous AGNs. Okay, so there's a characteristic like feature in the spectral index of these systems. They have kind of a flat 2-point spectral index around minus 0.5, and that distinguishes them from the spectral index of like hotspots and jets, which tends to be like steeper than minus 0.7. So by looking at the spectral index, you can actually find these compact sources like these black holes. And in 2001, Berg Spolauer did this work where she actually used like the data of more than 3,000 radioluminous AGNs from the from VLBI, and they were able to find only one source, double source, and this double nucleus was the one that had already been detected. Okay, so out of like 3,000 radioluminous, they were only able to find one double source with like small separations, and that allowed her to suggest that the time like this binary black holes span from the moment of like violent relaxation when the galaxies are merged to the point where they get to this stale radius. This stalling radius is less than like half a giga year. Okay, so they were able to put some constraints on the time scale for this process. So now I'm gonna show here like what they actually Rodrigues et al. Actually measure for the galaxy we're gonna be talking about. Like so, here is the center of these of the galaxy, and the zoom. You can see here that we're looking at milli-arc second distances. So that probes like parsec scales, okay? And if you look at these two regions right here at higher frequencies, 8 gigahertz and 15 gigahertz, and using their like spectral index mapping, they were able to identify those as like a binary black hole, okay? So in this talk, I'll talk mostly about the halo hosting this radio galaxy, which contains these binary black holes. So this is like a 10 kilosecond Steve Murray's GTO Chandra observation plus a 90 kiloseconds by Roger Ramoni. So we have good data, like 100 kiloseconds of data in this X-ray halo, and the redshift of this halo is 0.05, so a nearby galaxy cluster, and So here I just present like like a 1 megaparsec side box, and here 128 kiloparsec side box to show the structure of the cluster. But the main point here is that we actually measure the emission measure profile of this halo, and using this equation given by Alexei in 2006, we can actually feed the parameters. It's a more, it comes from a beta model, but it has like more parameters, it's more complex. It can actually take into account some deviations in the normal beta model profile. So we were able to feed like the density profile for this halo. And using the density profile for the halo, we are able to compute the 3D real temperature profile by deprojecting the temperature. So here in the red box, I present the equations that give me the red curve right here, which is the 3D temperature profile. And by projecting the 3D temperature profile by weighting by gas density, and the gas density comes mostly from this equation right here. So by projecting along the line of sight the 3D temperature profile, we get like a 2D temperature profile that we can actually compare to the data points. So doing that like in several steps, we were able to recover the 3D temperature profile. And we can see that this is a cool core cluster, okay? So the temperature in the core is much lower than the peak temperature. And that's a signature of a relaxed system, okay? Using the temperature profile and the density profile, and assuming hydrostatic equilibrium, we can actually compute the total mass. And the assumption for hydrostatic equilibrium here is valid because, as we showed, like this is like a relaxed cluster. Like when you look at the morphology, it looks like a very round like cluster. And when you look at the temperature profile, it indicates it's an indication of cool core, typical of relaxed clusters. So by using the hydrostatic equilibrium equation for the total mass, we get this curve right here, so for the total mass. And integrating the density, we can actually obtain like the gas mass. So the values we obtain is like R500 of typically a megaparsec, a gas mass of like 2.24 times 10 to the 13, total mass of like 2.53 times 10 to the 14, and a gas fraction of 0.09, very typical of like cluster of galaxies, 10% gas fraction, and a temperature of roughly 5 keV, and a luminosity, X-ray luminosity of 10 to the 44 ergs per second. So now we have like the overall properties, the basic properties of the cluster, like the total mass, the gas mass, and we can actually try to find signatures of perturbations in the core of the cluster by looking at the density, at the surface brightness profile. In the case here, given by these two curves correspond to the two wedges. We look at for the surface brightness profile in several wedges, but these are the regions where I actually found some jumps in some discontinuities. So here I plot the density profile for this model right here, that when integrated along the line of sight, the square of this, you get this surface brightness profile, okay? And the same, so on the right side here, we have the southeast wedge, and on the left part side, we have the northwest part of the northwest wedge. So when you look at the numbers, we get like a density jump. So this ratio here, the density jump of roughly 1.6, and when we measure the temperature inside and outside, we get like a temperature jump of half. Okay, so combining both, we get like something like a pressure jump consistent with being like close to 1, which is typical of cold fronts, not mergers. So in mergers, the pressure jump would be higher. So when it's consistent with being 1, it's a cold front, okay? So that's a signature of cold fronts. And if you look here more carefully, you can see kind of like a sloshing pattern in the center. I'm going to show another image later. that will show that better. But anyway, like we have like these numerical simulations, high-resolution numerical simulations by Askazibra and Markovich 2006, where they actually discuss the fact that an infalling subcluster with non-zero impact parameter will make the cool gas of the main cluster to acquire angular momentum and create this spiral-like feature of cold fronts due to this sloshing. So when we look at their simulations, going from 1.6 to 3.8 giga-years after pericentric passage, we see that like the spiral pattern develops and has like very different shapes as time goes by. And we can use those shapes to actually constrain or to actually have an indication of when the structure that caused like the sloshing actually flew by the main cluster. So here I present like the residual image of 4C 3711, okay, and the residual image of the Perseus cluster in the same physical scale. And you can see, like here it's easier to see, but you can see the same kind of structure here in the core of 4C 3711. We're gonna use this pattern to actually infer or to have an idea of the time scale since this sloshing occurred, okay, it started. So I flipped the previous like simulation snapshots just to present in a similar direction as we see in the Perseus cluster. And that happens roughly around 2 giga-years. So this spiral structure, which is similar to the one we find in Perseus and in 4C 3711, happens roughly 2 giga-years ago. The other interesting fact about this cluster is that it is a fossil cluster. The galaxy in the center has a magnitude much higher than any the luminosity of the galaxy in the center is much higher than any galaxy around it. So it is an indication that this system has been in that situation, like relaxed situation, for a long time. And whatever caused the gas to slosh happened more than 2 giga-years ago. If any major interaction had happened in between these 2 giga-years and now, we would have like a different, more perturbed like morphology for these galaxy clusters. So our conclusion is that the supermassive black hole in 4C 3711 is not a young black hole. They have stalled outside the present orbit of like 7 parsecs for several giga-years. And when we compare to the numbers that were presented before, it's longer than the time scale, the typical time scale from this initial like merging of the galactic stellar core to the point where they reach the stalling radius. That's it. Thank you. This one?
Yeah. I mean, you see the lobes, right? And you see the central source. So my question is like, so if you have a binary black hole at 7 kiloparsecs separation, you expect them to go around some kind of common center of mass or orbit because they're pretty long, is what you're arguing. So I find it hard to reconcile with the fact that the radial lobes are so regular, because if they're on a regular orbit, this lobe should be kind of like S-twisted.
Oh, but I don't present it here, but they present in the original paper from 2006. Like they have the imaging in several epochs, so they're able to measure the movement, on the plane of the sky, the movement of the sources. So they can actually see that there is like a radial movement of, like they can show all the components. I can show you that later, but they have the movements of all the components in this image right here. So apparently the center of mass is very close to C1 here. Okay, it's much more massive.
But then why are the radial lobes so regular? Because that doesn't indicate there's a motion going on.
And I don't know the reason for that, but and the motion that they show is actually not going north, but going in this direction, southeast. Okay, I can show you the image later. But they present the motion on the plane of the sky because they have several like observations in the past decade, so they're able to do that.
So, following up Reinhardt's question, is there an estimate for the orbital period of the binary black hole?
Yes, like I don't know off the top of my head, but in the paper they present the motion and everything. They present that.
And then if you back up to your table,
This one?
no, the other table is yeah, that one at the bottom. So it looked to me,
This one?
the one with the luminosity,
Ah, this one.
it looked to me like the luminosity is too low for the temperature. Does anybody put this on a temperature-luminosity relation? I would have thought the luminosity would be, for a 5 keV cluster, I would have thought the luminosity would be more.
Okay, I'll check.
Looks like it's really far off.
Oh, but sorry, I didn't write it here. This is within 500 kiloparsecs, not the R500. So okay,
But still,
yeah, I'll check.
because that's less than the luminosity of the Virgo cluster, whose temperature is 2 keV. Just seems like
Okay, yeah, I'll check.
a match.
Hey, can you go back to the final slide? So, if I understood correctly, there was already a problem of this stalling radius that if everything was stalled there, it's hard to get to the point where the gravitational
Radiation.
is driving the rest of the merger.
Yes.
And now it seems like you're saying that the analysis that you've done here indicates that you don't even get to the stalling radius. It stalls even earlier at a larger separation. Is that?
No. The separation is the separation for the stalling radius, but the point is that it typically, like what you infer, the time scale is half a giga-year from the moment of like the merger of the galactic cores to the moment that they reach this stalling radius. And from what we see here, these binary black holes have been at like larger separations for more than a few giga-years. So it's a larger time scale from the moment of the galactic merger to this stalling radius of typically like a few parsecs.
So I understand that then I would say in the second line of the box there, it didn't stall outside the present orbital separation. It just went slower.
Yes, yeah.
That's what I was confused by.
Okay, I'm sorry, like for the phrasing.
Yeah, so to get the age, you do a pattern matching to those simulations. Is the simulations set that you're matching to, does it span all sorts of parameters, of impact parameters?
Oh, it changes, like we have different vector parameters. We have different like mass ratios between the main cluster and the infalling subcluster, but the pattern is not very sensitive to those parameters. The size and
Next I'm looking at what is the uncertainty on that age. Could it be 1 giga-year? Could it be
yeah, it could be like a giga-year, yes.
could it be half a giga-year?
No, so
That's what I'm trying to, I guess you need a feel for the error bar on that age estimate.
yes, yeah.
We know how significant this is.
It could be 1, could be 3, but not half, and not 5.
Yeah.
Okay, but one should demonstrate.
Just like a quick like comment here. I think to demonstrate that like precisely, we have to actually, that's the hard part of it. We need to find the perturber for the system, and this is very hard to find. So, because we could do like matched numerical simulations to actually infer what is the time scale. But we're comparing, since we don't know what the perturber mass is, and it's not that simple, like just by looking at other numerical simulations to infer what is the uncertainties.
If you set it on this, what's the current projected separation?
So it's 7 parsecs. You had a question. Yeah.
Oh, yeah.
Go ahead.
Thank you.
I'm sorry.
Going back to the beginning of your talk, you discussed how sources in this category are identified, and pointed out that a way to do it is by an anomalously flat radio spectrum.
Yes.
So I was wondering, is there a clear physical reason why that is the right identifier?
Oh, I'm sorry. Maybe Laura can or Rainer can.
That's because you get synchrotron self-absorption in the nucleus because it's so compact. So it gets self-absorbed in synchrotron, because essentially the spectrum becomes flatter.
Okay.
So it's a very compact source. If you have an extended source, you get steeper.
Sorry, that was outside my field of expertise. So there was another question. You?
Any other questions?
Oh, right up there.
So just to be clear, are you claiming that the current binary black hole is related to the current sloshing pattern?
No.
Oh, so this is complete.
No. So whatever caused the sloshing happened more than 2 gigayears ago, and whatever brought the 2 supermassive black holes together happened even earlier than that. That's the claim, because it looks very relaxed cluster, and whatever caused it, the only mild disturbance that we see in the X-ray emission was caused by the sloshing more than 2 gigayears ago.
If there's no any other questions, thanks, Billy.
This one, right?
What's that?
You need this one.
Idan graduated from Dartmouth College, and he's currently a ITC postdoc fellow, and a postdoc.
Sorry.
And his research has been focusing on hypervelocity stars. Today he's going to talk to us about the Galactic Center.
Do I need to put this on? All right, everybody can hear me? All right, thanks everybody. So this is where we live. This is our galaxy. So the region I'm most interested in, or at least I'll talk to you about today, is going to be the very center of our galaxy. When I mean very center, I really mean the very, very center, sub-parsec scales. Now, decades ago, if you were to talk to an astronomer and say, the center of our galaxy is fascinating, there are all these stars, it's its own solar system, they probably would have just thought you're some crazy person. But it turns out that, in fact, using infrared and also radio, we know that the Galactic Center is incredibly dense. There's 1 million times more stars than there are around the sun, and it's a fascinating region. And the star that approaches the Galactic Center, Sag-A, at which you'll see it come by pretty soon, is star S2. And really, this star, S2, is sort of the smoking gun that there is a supermassive black hole at the center of our galaxy. Now, this supermassive black hole is also, very, produces all kinds of phenomena, including X-rays. In 2013, there was the brightest X-ray flare, 10 to the 39 ergs. The question still remains, why are there all these flares coming from the center of our galaxy? Is it some collimated outflow, magnetic reconnection, or tidal disruption? I will concentrate on the last one because I think that's pretty interesting, and it relates to some of the work I've been doing. And of course, Sag-A has been known for decades. Even before we knew there was a supermassive black hole in the center of our galaxy, we've known that it's a powerful radio source. Depending on what frequency you're looking at, it can be, it is definitely one of the brightest radio sources in the sky. It's a fascinating region. What powers this radio source? Just like many things in astronomy, that's debatable. Okay, so I'm going to concentrate mostly on stars. This may be one of the lowest energy, high energy talks you'll ever attend, but hopefully you'll still find it interesting. So this is amazing work done by Andrea Ghez and her group at UCLA, which is, as I said, the smoking gun that you have this Keplerian orbit. In fact, now you have 2 full Keplerian orbits to tell you, okay, in the center of a galaxy there is something that's 4 million times the mass of the sun. The only thing it can be, is a supermassive black hole. And how do you get stars like S2 so close to a black hole? That was actually not known for a while, but this video will show you how it's done. You start with a binary system. If the binary gets close enough to the black hole in the center of the simulation, then you have a tidal disruption. One star falls into the gravitational well of the black hole, as shown here, and the other star could be ejected as a hypervelocity star. And this is work that Avi Loeb and I, did back in 2006, and 10 years later, it still seems to be the correct reason, the most really about the only way to explain how you can get a star so close to a supermassive black hole. These stars, by the way, are not tidally disrupted. So although tidal disruption events are fascinating, these stars like S2 are not tidally disrupted. We do not see any evidence of tidal disruptions from them. Anyway, this is some more from our simulations, and in each case, you get these really tight eccentric orbits around the supermassive black hole, just as you see, just as we see in real life. Okay, so why do we want to study these S stars? Well, of course, they put constraints on the environment around Sagittarius A star, and I'll talk a little bit more about that soon. They give us better stellar orbital measurements. We might actually be able to find new stars, since the stars that we see are only the brightest. It's a selection effect. The stars that we see in the Galactic Center are only the brightest stars, but there's numerous more. And also testing GR. This is something that's, of course, we've been doing for decades, but we want to test GR in the extreme gravity regime. And stars near the supermassive black hole are one of the few ways you could really do it. Okay, so let's take a look at S2 again. These are the orbits. So this is work done by Stefan Gilson at the Max Planck Institute. And as you can see, it has this beautiful Keplerian orbit, but it's not there is perturbation involved here, and this perturbation is one of the ways to actually test strong gravity, and I'll talk a little bit about that in a bit. So we want to talk about strong gravity, but aside from testing GR, there's another interesting thing. If you can imagine a star like S2 as it's going through the Galactic Center, really near Sag A, that there's an accretion disk around the supermassive black hole. This star is going at a tremendous velocities. Around peri-Botox, it's about 5,500 kilometers per second. So, at that velocity, it's going to produce a substantial shock, and this shock is going to emit a lot of synchrotron emission. This is work that I recently did with Xiaowei Wang, who's also one of Avi's grad students. And we looked at a whole bunch, I'll show you some graphs in a second, but we looked at a whole bunch of scenarios. And this work, I will admit, there's just a lot we don't know. For example, we don't know what the fraction of the shock energy going into these electrons. We don't know that much about the magnetic field. There's just a lot you don't know about the Galactic Center because it's a very difficult region to study. But nonetheless, if we use sort of canonical numbers, we find that you can expect a pretty strong emission in the radio from a star like S2 around the Galactic Center. So here we have in the black dots with the error bars are actually the emission, from Sagittarius A star. And the lines represent different winds that we chose for a star like S2. So this is synchrotron flux versus power, and basically what we said is, look, there's a good chance you may be able to spot a star like S2 or hitherto unknown star using radio waves. And again, why is this important? For testing strong gravity, finding new stars, and all, and everything else that comes with it. This is work we did in 2015, but now I'm going to take you back to, so these are the stars orbiting the Galactic Center. I'm now going to take you back to the companion star, which is a star that's being ejected from the Galactic Center. So hypervelocity stars are, are basically the companion to like S2 that's being ejected. And they also provide a direct link to the Galactic Center. It was known since they were discovered back in 2005. They could even be used as dark matter probes. And more recently, I wrote a paper on planets, which is kind of interesting. So first of all, how do you get a hypervelocity star ejected so fast? Again, it's just conservation of energy is all it is. Falling into the gravitational well of this massive black hole, it's a lot of energy. When the binary star is disrupted, the companion gets a kick. If it's sufficient, it'll be unbound to the entire galaxy. So back in 2012, I did some work, again with Avi, and we said, what if there are planets around these hypervelocity stars? We know of 20 hypervelocity stars so far and about 80 hypervelocity star candidates. So these things are real. What about planets? I mean, nobody's done work. Could there be planets around these things? Well, there might be. And if there are, what do you get? So it turns out that, just like hypervelocity stars, you could expect to get planets shot out of the galaxy. Typically, it follows a similar pattern to the hypervelocity stars. In other words, if a hypervelocity star is moving at roughly 1,000 kilometers per second away outside our galaxy, you would expect a planet to move at roughly 1,000 kilometers per second. Except in certain instances where because you have a binary star with a planet around it, you can have this kind of slingshot effect where the planet could actually be ejected at almost 5% the speed of light. So that was kind of unexpected, and that was kind of an interesting discovery. And that got us a bit of a press release because I guess the public likes things that move really fast. So if you're desperate for a press release, try to do something fast. And but that wasn't the point of the paper, was that you could have planets being ejected at high velocities. The point was that you can have hypervelocity stars with the planets still in transit. So a transit, as I'm sure most people know, is just when a planet crosses in front of the surface of the star and we see a dip in light curve. Okay, so you can have these stars being ejected out of a galaxy. They can have planets around them. So we said, hey, you may be able to find a transit around a hypervelocity star, and if you can do this, it's all but indisputable evidence that there are probably planets in the galactic center. In fact, otherwise, how are you going to find a planet in the galactic center? It's pretty much, well, at least for now, it's impossible. I don't know any way to do it. Our instrumentation is not even close enough. But if you can see one around a hypervelocity star, and if they do exist around hypervelocity stars, the probability of seeing a transit is actually pretty good because it's going to be a very tight system. If you do see one, that's indicative that there are planets around the galactic center. And why is that important? Well, it's important for planetary people because they want to know how ubiquitous planets really are. But also, it turns out that it may solve this notion of where X-ray flares come from in the galactic center. By the way, this is kind of a little plug-in for a paper I just finished with Giacomo Fragione, who's another grad student. We basically looked at a whole bunch of, looked at planets around runaway and hypervelocity stars, and we did all these interesting simulations. And we actually predict that TESS, some of you may be interested in TESS, and also Gaia, maybe some of you are interested in Gaia, will eventually be able to find some of these planets around hypervelocity and runaway stars. At least one, hopefully more. So what are the possible outcomes? So if you have a planet around a star in the galactic center or around a hypervelocity star, it's always possible for the planet to collide with the star, in which case you see an enrichment. And there could be a whole swarm of planets, according to our research, around the galactic center. And in certain instances, maybe these planets get close enough to the black hole where they're tidally disrupted. We're not the first to have actually thought about tidal disruptions. So, the flares that we see from SAT-J, well, we don't know why we see them, but some people think that they're due to tidal disruption of asteroids. Perhaps. That's certainly a possibility. But where do these asteroids come from? Why should there be a whole bunch of asteroids in the galactic center? So Avi and I thought perhaps the most likely scenario is they come from planets. Maybe parts of the planets are either ripped off, you can have collisions. It's such a dense environment. This would at least explain what's happening here. Furthermore, if a whole planet is disrupted by the supermassive black hole, you would expect a very strong flare. 10 to the 39 ergs was the strongest flare observed so far. We predicted a planet would be closer to 10 to the 41 ergs, but that's still a lot less than a star, which should be on the order of 10 to the 43 ergs. So anyway, so this is something to test, and maybe in the future one of you will discover, a planet in the galactic center. And of course, this is only theoretical. It turns out theorists don't know everything. Back in 2012, Stefan Gilson and Max Planck discovered G2. You may have heard of G2, this cloud going to the galactic center. It was going to be incredible. It was going to produce all these flares, and you're going to see all these amazing things. There's going to be all these fireworks. It got all this press release. And then at the end, G2 did nothing, absolutely nothing. Why? That's a bit of a debate, but the point is we don't know everything. There's always something new to be discovered. And so I know I've gone through things pretty quickly, but just some concluding remarks. At least some of the S stars, in the galactic center are definitely former companions to hypervelocity stars. A star such as S2 around the galactic center, should be visible in the radio, which is important for lots of studies that I've explained. And there could also be planets around hypervelocity stars and around Sagittarius A star, and maybe at some point in the future we'll even detect one via a flare. Okay, thanks everybody.
So you said that S2 may be visible in the radio, but
Yeah.
could you not say is visible or is not? Because are there not this observation? Because you show S2 made a full.
Yeah, that's not actually something so simple to do. I'm actually working with some radio people on that. It's actually not as trivial as you might think. It may be, it's a very eccentric orbit. So it's not like it's always near Sag A. It's a very eccentric, and most of the time you wouldn't expect that strong a synchrotron emission. But when it gets near pericenter, you do expect a strong synchrotron emission. And in fact, it's right now approaching pericenter. So the question is, will we be able to see it soon when from like VLBI measurements, etc.
And would the time scale work for this acceleration process? Because you need some time to. I assume you start from some thermal electrons and then you have to accelerate them.
Yeah, no, it should. According to it, absolutely should work. Yeah.
Okay, because it only spends like what you said, like a very short time.
That's right. But nonetheless, yeah, you should see actually a very strong shock.
Any other questions?
Can you be sure that all the hypervelocity stars are actually from the central black hole?
Yeah, that's a really good question. So actually, Warren Brown has done a lot of studies in this. So he predicts that pretty much almost all the hypervelocity stars except one are well, he says most likely from the galactic center. Now, you're absolutely right. We can't be certain, but we're certain that one star is definitely not from the galactic center. But according to Warren's studies, all the other hypervelocity stars are almost certainly from the galactic center. So hypervelocity stars, about 20 confirmed and about 80 candidates.